Alright, so in today's video we're starting out finishing off, before we started off with some construct applications of inverse images of manifolds with constructions you can make with them, that kind of thing. And we didn't get quite all the way through it, so we're going to look at the last couple of constructions first in this video. Starting off with, transversal morphisms. So, first off, we have two morphisms of the form fi, I being 1 or 2, from a matching yi to x. And now we define y1 times the x product, I guess, of y2 to be the set of pairs in the Cartesian product of the domains of the functions whose images match up. There's a category theory name for this, isn't it? Isn't this like the pullback or something? They call it here, in this context, this is called the fiber product, which is a term I've heard before. Fiber product of y1 and y2 over x. Now, let the ith projection I from y1 fiber product over x with y2 to y of the respective I be the restriction of the projection, ith projection, to obviously the x fiber product of y1 and y2. And we're going to let f be the composition of f1 with p1, which is equal to f2 times p2. So just to better visualize what's going on here, we have y1 times the x fiber product of y2. We can project it onto y1 or y2, and then apply your existing morphism from y1 to x or y2 to x. And not only are these equivalent to each other, these are equivalent to our function f by definition. Now we're going to let y1, y2 be in the x product of y1 and y2 fiber product. Let x be the image of this point under f. We say that f1 and f2 are transversal at y, being of course y1 and y2, if the tangent space at x of x is equal to the image of the tangent space of y1 on f1 plus the same for the other spot. This brings us to a theorem. So suppose we have such an f1, f2 being transversal at y. Then we have a few consequences. First off, we can extend this transversality to all points in a neighborhood of y in y1 x times y2. Secondly, the x fiber product of y1 and y2 is locally a submanifold of the product of y1 and y2 at y. And third, and finally, the tensor space at y of y1 x fiber product of y2 is equal to the fiber product of the tensor space of y1 and y1 across the tensor space of x and x with the tensor space in y2 at y2. So, proof, we're not going to do a thorough proof, it's more just like an outline. But if we set y to be y1 times y2 and z to be the fiber product across x of y1 and y2, and we're gonna set delta I to be the map from y to, we're going to let be delta I from y to y times x as the pairing of the identity and the composition of the morphism from y to x on the relative function on the relative projection. And we're going to let delta be the restriction of these delta i's to z. Then, first off, delta 1 and delta 2 are isomorphisms of y onto submanifolds of y times x. Secondly, delta 1 of y and delta 2 of y are transversal at delta of y. Third is delta of z being delta 1 of y and delta 2, the intersection of delta 1 of y and delta 2 of y. And that's just kind of like all the building blocks. I'm not going to try to work out all the finer details here. And it's also worth noting if some Fi is a submersion, it doesn't matter which one. F1 and F2 are everywhere transversal. And our last construction is close related to this, more just like a side note, which is on mixed transversality. So if in E, in the setup we have, F1 is an inclusion of a submanifold y1 into x. We also say F2 is transversal over y1 at y. F1 and F2 are transversal at y. Alright, and that's kind of what we left out last time. It's a nice opening third, hopefully, for a video. And so this is all like inverse images. Our next section, we're carrying on with construction of manifolds, but this time we're now going to be focusing on quotients. So let X be a manifold and R in their product being an equivalence relation. So we're going to let X over R be the set of equivalence classes equivalence classes of elements of X under R and let P, the map P from X to X over R, be the projection you'd expect. So give X over R the quotient topology, which, as we recall, where a set U bar in X over R is open, said to be open if the inverse of the projection, the inverse image of U bar is open in X. Alright. So this gives us a topological space based on the quotient of our manifold with an equivalence relation. We kind of need a bit more for it to be a manifold though, right? Which brings us to a theorem. If there exists a manifold structure on X over R such that P is a submersion, then this manifold structure is unique. And the proof is actually pretty easy. We saw for all Z, the morphisms from X over R to Z is determined by the manifold structure of X, and as we saw, the set of morphisms from topological space to every possible codomain uniquely determines that space, and so we're actually done with just that. So when this sort of manifold structure exists, that is, when we have the projection from the map to its quotient being a submersion, we call X over R with this structure a quotient manifold. Of X, with R now being called a regular equivalence relation on X. Now we have another theorem to follow this up. This one is by Gödemel, I'm guessing it's pronounced. Probably not very close. Which is just the following are equivalent. First off, X over R is a manifold, which is, just by definition, saying that R is regular. And so we just kind of need a better way to understand these, and so the equivalent condition, first off, R is a submanifold of X times X, and secondly, the second projection from R onto X is a submersion. Let's look at the proof. So we want to show that first off, if X over R is a manifold, we have these conditions. First off, we get this commutative diagram. We can project R onto X in two ways, because R is a subset of X times X, so we can project from either component onto X and then map by P onto X over R. This gives us the set R is equal. We also see that the set R is equal to the fiber product over the quotient of X and X. since P is a submersion, this gives R as a submanifold of X times X by previous results. Now if you haven't compare X and Y and R, and we have Z being their image, which has to be the same, we know, because we want to quotient these things out anyways. One has, and we have that, the X tangent at R being the, by our previous formula, it's going to be the X tangent of X with the fiber product of the tangent at X of X over R. That's going to be Z actually. Over X over R with the tangent space at Y in X, which gives us that the map from the tangent at R at X and R to the map the tangent at Y at X. Once again, that is a Z. X does not make sense since X is in that also, wow, how did I just write that down without thinking about it? Whenever I have a tangent in R, it's going to be Z in this context. Tangent and R. The map from the tangent at Z of R to the tangent at Y of X is surjective. Hence, the restriction of the second projection to R is a submersion. And 2 to 1 is by 6 lemmas, it says. So that's going to be fun. We'll be working through that. First off, we need to see, suppose U is a subset of X. We're going to set R of U to be the intersection of U in the product of R, the intersection of R with the product of U with itself. And recall, U is said to be saturated with respect to R if we can project U and then inverse project it and then get U back. Now, so let's go through our lemmas now. First lemma, let X be the union of some UI where UI is an open saturated subset of X such that the quotient of UI with R of UI is a manifold. And then X over R is a manifold. And the proof. By hypothesis, The map from U of I, each U of I to U of I over R U of I is a submersion. Hence, the manifold structures induced on the quotient of the intersection of Ui and Uj with R of Ui intersecting Uj by Ui over R Ui. This is for any I and j, and by Uj over R Uj agree for all I and j in our indexing set. Hence, there is a unique manifold structure on X over R compatible with the given structure on Ui over R of Ui, and we also need P is to be a submersion since its restriction to Ui is a submersion for all I. Alright. Those are two conditions to be a manifold by a quotient. So, second lemma. P is its map, P is open. That is U being open in X implies that P inverse of P of U is open in X. And the proof. Well, for an open U, P inverse of P of U is the projection, the second projection of U times X intersect R, which is open if U is open, as PR2 is a submersion. Alright, let's go on to our next lemma here. Let U be open in X. Suppose that P inverse of P of U is X. And that U over R of U is a manifold. Then X over R is a manifold. And we got a proof of that when my hand is okay. Proof. The canonical map alpha from U over R of U to X over R is bijective. Hence, if we have that the map we're going to call beta to be the inverse of alpha on P from X to R over U. I mean U over R of U, not R over U of R. That doesn't make any sense. Is a submersion we will have by transporting the structure of U over R of U to X of R. We will have that X over R has a manifold structure such that P is a submersion. Now we have a diagram to look at our situation here. We have U times X intersect R. We can project this onto its first component by first projection onto U, or by a second projection. Why did they draw it like this? Hang on. We can project it onto its first component as U, or its second component as X. By U, we can get it to the restriction of U. Get it to U over R of U. By the restriction of beta to U, from X, we can just use all of beta. From this, we see that beta composed with U on the first projection, which is just beta on our second projection. This is a submersion. Since our second projection is a submersion, beta is a morphism, and in fact, a submersion. Fourth lemma, lemma 4. Okay. So 1 sec, I just want to skip. We're halfway through, so I just want to scout out how this is going to go. Okay. Let X be the union of UI, where UI is an open subset of X for each I, such that UI over R of UI is a manifold. Then X over R is a manifold. Okay. They don't even list a proof for this one. I think it's more immediate from our previous results. Sorry, get that out of the way, so you can attempt to read my writing. But the point of this lemma is to kind of make constructing a manifold structure on a quotient local. And then we're just going to solve this kind of local problem with our next two lemmas. So we will aim to show, we will now that for x naught in x, there's a neighborhood of x naught in x of x naught in x such that U over R of U has a manifold structure such that U onto U over RU is a submersion. So essentially we have this way now to split up our quotient into its pieces with this RU construction. And we know that we can build a manifold out of like pieces with this previous lemma, so we just gotta do it now. So lemma number 5. We'll let an element x0 and x. There exists an open neighborhood U of x naught. There's a manifold W of U and a morphism R from U to W such that if U is an element in U, then RU is the unique point the unique point of W equivalent to U modulo R. That's the proof. So let n be the set of tangent vectors C in the tangent space at x naught of x such that C comma 0 is in the tangent space of x0 comma x0 x0 comma x0 of R. We want to choose a submanifold W prime of X such that X naught is in W prime and K is the tangent at X naught in W prime, the tangent space. We want this to be a complementary subspace to n in the tangent space of x naught at x. And then finally, we're going to define the capital sigma to be W prime times x intersecting R. Then we want to show, first off, sigma is a submanifold of R. And secondly, the second projection from sigma to X is a tall. At x0, x0. Now A follows since sigma is the inverse image under a map C, which we're going to define of W, where C denotes the first projection from R onto X. And we use for this, we use our previous result with the hypothesis that our second projection is a submersion, and R, of course, is an equivalence relation. Next, we got to see that we see that the kernel of T of the second projection at x naught is just going to be the intersection of n and k, which is 0. So the tangent at a rubber of PR2 is injective. Now we want to let eta be in a tangent vector to x naught at x, and we're going to choose a xc in the same space such that their pairing xc eta is in the tangent space of x naught, x naught in R. We're gonna decompose xc as xcr. No, the component of xc in n plus the component of xc in k. Then we get that ck comma eta is in the tangent at x naught, x naught in R, since n is contained within this tangent space. Then k eta belongs to t set x naught w prime times t x naught x intersecting t x naught x naught of R, which is going to just give us t x naught of sigma. And this element maps onto eta. So T of our second projection is also surjective. Thus, there exists open neighborhoods U1 and U2 of x naught such that the second projection of the intersection with sigma and u1 times itself onto u2 is an isomorphism. With an inverse, we're going to denote f, which must have the form f setting x in R2 to r of x comma x. Notice that u2 has to be inside of u1, and that if some x is in both u2 and w prime, then r of x has to be x. And this is by the fact that x comma x and r of x comma x are in both in the intersection of sigma and u1 times 1 u1 with the same image in u2. Now, finally, we're going to set u to be x in u2, and the notation here is weird. I'm just going to copy the weirdness. R of x in both u2 and w prime. And we're going to set w to be the intersection of u and w prime. And with u, w, and r as required in the lemma. I guess, nah. Then u, w, r are as in the lemma. If you recall the statement here, if you can read that again. So our two conditions we need to meet from that. First off, r has to carry u inside w, and secondly, Rx is unique in W in being equivalent to X for X in U. For part A, we see that for X in U, for X in U, Rx is in U. That is, R of X is in U2, and R of X is in the intersection of U2 and W prime, as R of X is going to be idempotent on X, which is going to be U2 intersecting W prime. And for part B, note there is exactly one point in R intersecting W times U mapping by the second projection onto X in R of X, comma X. That is our fifth lemma. And there's one more lemma, and then we are finally free. Lemma number 6. Thankfully this one's much shorter. If we have UWR as in number 5, then U over RU is a manifold. And the proof. The map, the morphism R from U to W has a right inverse, being the inclusion of W into U, hence is a submersion. In the commutative diagram, U mapping by R to W, mapping by alpha, U onto RU, this being of course the projection, and here alpha is a bijection. So you're done by transporting the manifold structure of W onto U over RU. Since, keep in mind alpha is a bijection, that's easy. And we close off this video with a remark. If R is regular, X over R is Hausdorff if and only if R is closed in X times X. Alright, and that's the end of this discussion. There is an appendix we probably will go through, maybe. Oh yeah, there's a bunch of stuff in the appendix. It looks all really weird and messy, so that's going to be fun. So join me for that next time. Thanks for watching.